Electrochemical cells is one of the topic that a lot of students find very challenging, and it's very common in paper one as well. So I will do my best to simplify this topic for you and give you all the exam techniques or give you all the information that you will need in order to answer the question that comes in the exam. So what is an electrochemical cell? How does it work? What are the components of an electrochemical cell? So an electrochemical cell is these cells which use redox reaction to drive electrons across the cell, and then it can convert this energy into different types of energy. The components of an electrochemical cell is that we're going to have two half cells. Each of these half cells will have an electrode of a different metal, and the half cell will be composed of an electrode of a certain metal immersed in an electrolyte, which is an ionic solution of that metal. For example, we could have zinc with zinc ions. So zinc ion, like we can have zinc nitrate, we can have zinc sulfate. So any ionic solution for zinc. And the other one will be a different metal as well, immersed in a solution of ionic solution of that metal, like copper and copper metal. Sometimes as well, we could have a solution that is a mixture of two different ions of the same metal. Like we could have a mixture of iron 2 plus and iron 3 plus, where the redox takes place and these two change in the reaction in the half cell. In this case, the electrode we use is going to be platinum. We don't use iron here. Otherwise, we are talking about a different redox reaction. So we would use platinum and in addition to the mixture of the iron 2 plus and iron 3 plus. When we will connect the two electrodes from the outside with the voltmeter, which can measure the voltage change. And then we can, or potential change, we have to connect the two half cells with something called the salt bridge. So the salt bridge will contain some inert ions. What we mean by inert ions, we mean that ions that will not react with either the first half cell or the second half cell. So basically, it can do like substitution reactions, but it doesn't actually undergo any redox reaction with any of these. Something like potassium nitrate, for example. So potassium nitrate ions will not undergo any redox with any of the ions in either of the half cells. So the role of the salt bridge is to allow the flow through the ions to flow through them and to balance the charges. So as you can see, for example, if we put potassium nitrate, the nitrate will move here and the potassium can move to the other sides to balance the charge on both half cells. So there will be a potential difference that will be generated because there will be on one half cell there will be a reduction a reaction, and on the other one there will be oxidation. So here we have the zinc with the zinc ion. This is called the anode, and the oxidation will take place here on the anode or the negative charge, where zinc will lose electrons to give zinc ions, and the electrons will start to flow through the circuits from outside until it reaches the cathode or the positive electrode, which is the copper, and the reduction will take place here. So here it's the oxidation, and here it's the reduction for the copper. So the copper ions will be reduced to give the copper metal. As we can see, we can represent the equation, the oxidation and the reduction. As we can see here, zinc will give you zinc ions plus 2 electrons, and the copper will gain 2 electrons, the copper ion, to give you the copper. We can represent this cell, this electrochemical cell, as follows. So we start with the oxidation reaction first, and we add the species that's going to be oxidized, which is the zinc in this case. And then we add the oxidized form of the zinc, which is the zinc ion. And then we have this line here, this line, vertical line, a small line that refers to the phase boundaries, because the zinc here is a solid and the zinc ion is aqueous. So there is a phase boundary, or there is a phase, these two are in different phases. So you have to show that by adding this small vertical line. And then we have these two vertical lines between the two half cells, and these represent the salt bridge. So this is the salt bridge in between. And then we would write the reduction half cell. So the reduction where we'll start with the species that's going to be reduced, which is the copper ion, and then don't forget the phase boundary and then the copper solid. So this is how you represent the electrochemical cell. Start with the oxidation and with the reduction. So how would we know which side is going to be oxidized, which one is going to be reduced? This is based on what we call the standard electrode potential. And the standard electrode potential is that we measure the potential of each mix of ions or redox reaction, how they can actually have the potential to be oxidized or to be reduced compared to hydrogen. So we have a reference electrode with a potential defined as 0. This is the standard hydrogen electrode. And a standard hydrogen electrode, because it's a standard, we have to have standard conditions because the different conditions can affect the standard potential that we calculate. So the conditions here are 298 Kelvin as temperature, 100 kilopascal pressure, and 1 mole per decimeter cubed for the hydrogen ion. The standard hydrogen electrode has the hydrogen as hydrogen gas, and it has hydrogen ion or hydrochloric acid as source of hydrogen ion with that particular concentration as an electrolyte. And then we have the platinum electrode here, and the platinum electrode where the different reaction can take place or the electrons can move around. And then this is the half cell, and this is connected to the other half cell, which is going to contain the oxidation reaction or the reduction reaction, which we would need to measure its electrode potential. So now we would use, this is used to measure the electrode potential of other half cells. So that will give us the electrochemical series. So an electrochemical series will arrange the different reactions, redox reaction, based on their potential to be oxidized or reduced. When you put the electrochemical cell, we usually write it in the reduction form, meaning we write the reduction reaction, not the oxidation reaction. Remember, these are reversible, but we write it and measure it as a reduction. So as you can see, all of these, the electrons are added here on the left-hand side, meaning these all are the reduction reactions. And then we measure the standard electrode potential. You will get a certain value. The value can vary from being negative charged until it becomes a positively charged. The positive charged electrode potential means that the left-hand side is more easily reduced, or that means this species or this reaction will be most likely to go through reduction. So it's going to be more as oxidizing agent. So here in this electrochemical cell, you can see in front of you, and this is taken from one of the past papers. You can see that the first one, the one with the highest positive value, which is oxygen being reduced to give water, this has the highest oxidizing power, or that means that the oxygen will be reduced. So if you have a half cell for this one with any of the ones below it, this is always going to be the reduction, and the other one is going to be the oxidation. And we can say exactly the opposite for the negative value for the standard potential. So the ones with the negative value, that means the right-hand side is more easily oxidized, meaning it will be more towards the oxidation. So the reaction will go the other side to the other side. So it's going to be oxidation rather than reduction. So as you go down from most positive to most negative, then the oxidizing power will be reduced, and as you go from the bottom to the top, from the most negative to the most positive, the reducing power would be reduced. So these at the bottom here with the most negative are the highest reducing, so there will be mostly oxidized, and these at the top with the highest positive charge will be the highest for to be the highest oxidizing, or they will be mostly reduced, so that it's going to be reduced. Remember that thing that is reduced is oxidizing agent. The thing that is oxidized is a reducing agent. And now we will calculate the EMF for any cell. The EMF should always be positive for a reaction to be feasible, for electrons to flow. How to calculate the EMF? You calculate the EMF using this equation. So we're gonna calculate it using the standard electrode potential for the reduced one minus the standard electrode potential for the oxidized half cell. So which one is reduced, which one is oxidized? The one that is reduced is the one with the more positive charge. The one which is oxidized is the one with the more negative charge. Or more generally, you could say that the one that is reduced will have a higher value of the standard electrode potential than the one that is oxidized. So for example, one of the exam question was asking why zinc, the zinc here, can actually be used to reduce vanadium 3 plus to vanadium 2 plus, but cannot reduce vanadium 2 plus to vanadium. To answer this question, you can look at the standard electrode potential for the reduction reaction from vanadium 3 plus to vanadium 2 plus, and you can find the standard electrode potential is minus 0.26. And this is more than the standard electrode potential for the reduction of the zinc 2 plus to zinc. This is the zinc 2 plus to zinc. That means zinc can reduce the vanadium, but the vanadium vanadium 3 to vanadium 2, but the vanadium 2 plus cannot do the other side. On the other hand, when you look here, you can find that to reduce vanadium 2 plus to vanadium, you would need something that would have a standard electrode potential that is lower than minus 1.2. And you can see that the zinc, the standard electrode potential for it is higher value. So it cannot be used to reduce vanadium 2 plus to vanadium. So what can be used from this table? It's magnesium. So you can use magnesium because the standard electrode potential for it is actually less than the standard electrode potential for the vanadium 2 plus to vanadium. And now we can calculate the EMF or electromotive force of the of this of any cell. So let's say we are going to calculate it for the vanadium 3 plus to vanadium 2 plus along with the zinc. Then it will be, now we know that this is the reduction and this is the oxidation. So it's going to be the standard electron potential for the reduction, which is minus 0.26. And then this is minus the standard electrode potential for the one that is oxidized, which is the zinc. So it's minus 0.76. And then you can actually calculate that and find the EMF for this particular cell, which is 0.5 volt. As you can see, it's in the positive value, which means this can actually be feasible. So what are the different things that can affect the EMF? In the exam, they wouldn't ask you to explain why the change in the concentrations affect the EMF, but they will ask you what would be the effect. So I'm only going to tell you what is the effect without explanation because you don't need to know it at this point. So we have two half cells. So we have the half cell where the reduction take place. So the reduction which happens at the cathode or the positive electrode. So if you increase the concentration of the half cell or the ions at the half cell where the reduction take place, that will lead to an increase in the EMF and vice versa. So if you decrease the concentration of the solution at the reduction, that will decrease the EMF. And we can say the opposite for the oxidation. For the oxidation reaction, if you increase the concentration of the ion at the anode where the oxidation takes place, then that will decrease the EMF value. And vice versa again. So if you decrease the concentration of the ions at the anode, that will increase the EMF. Also, the pressure can play a role. So increasing the pressure will decrease the standard electrode potential. This is why we need to measure everything under standard conditions. So the standard electrode potential, as we said, this is how we calculated. So the standard electrode potential, because this is very common in the exam, not just in paper one, but also in paper three in the multiple choice questions. Now we should know how to calculate that, and then how to write the equation for how to write the representation of the cell. So as you can see here, we have two reactions. The first one is the oxidation of iron to iron 2 plus, where we have the iron as a solid. So this is the half cell where the oxidation takes place, and then we added the phase boundary. And then this is the salt bridge, and then this is the other reaction where the reduction takes place. So we start with the species that is going to be reduced, and then the reduced form. These two are aqueous. None of them is in a different phase. So we didn't add a phase boundary here. We just added a comma in between these two, but we have an electrode of platinum. Even if they didn't say it, you can state it, then you will have to say it in the representation. We added the phase boundary, and then we added platinum at the end because we will have to have a certain electrode, which is mostly platinum. So this is how to write it. And it's very common in the exam to ask you to give the conventional representation of the cell. Then the commercial electrochemical cells, the one that mostly come in the exam are the rechargeable one, the lithium ion batteries, and the fuel cell or hydrogen fuel cell. So lithium ion are these rechargeable cells which you can use and then you can recharge, like the one that you use with your laptops or with your mobile phones. So the electrodes here for the lithium ions are, you have a positive and negative electrode or a cathode and anode. So the positive electrode or the cathode is lithium copper oxide, and the negative electrode here is graphite. The electrolyte is lithium salt in organic solvent. So there are two equations here, and both of these we're gonna write them in the reduction form because we're gonna refer to the standard electrode potential. So the lithium plus will be, when reduced, it will give you the lithium atoms. And then the other one is the lithium ion reacting with the copper oxide and gains electrons to give lithium copper oxide. And the standard electrode potential for the first one, as we can see, is minus 3.04 volt. This is and the second one is plus 0.56. So which one is going to be oxidation? Which one is going to be reduction? This one has lower value, more of a negative charge. So this is going to be the oxidation, as we can see. And the other one is the reduction. So what happens at the anode here? We're going to have to write the oxidation. So it's lithium giving you the lithium ions plus the electron. So this is what happens at the anode, and the other one at the cathode will be this reduction reaction. And then what happens in the recharge? When you recharge the battery, you reverse the both reactions. So the oxidation will be reduction, and the reduction will be oxidation in order to reverse these two reactions and then recharge the battery. And then finally, the hydrogen fuel cell. So hydrogen fuel cell will use hydrogen and oxygen to give water and generate electricity. So in this case, we're going to have the hydrogen, which is going to be fed into the anode and the oxygen into the cathode. So the hydrogen at the anode is going to be oxidized, and you need to know the equations, half equations. So hydrogen will be oxidized here by reacting with the hydroxide ion because the electrolyte here is potassium hydroxide. It's alkaline hydrogen fuel cell, and that will give you water and electrons. And then the oxygen, on the other hand, will be reduced by reacting with water and with the electrons to regenerate the hydroxide ion. The overall equation for that will be hydrogen plus oxygen gives you water. And whether we use the alkaline electrolyte or alkaline hydrogen fuel cell or acidic hydrogen fuel cell, the potential will be always the same because the overall reaction is the same because this was one of the past paper questions. The hydrogen fuel cells have their advantages and disadvantages. So what are the advantages? The advantages is that you don't need to recharge it. So as long as you have a continuous supply of hydrogen and oxygen, you're going to generate electricity. The electricity is generated and water is the only waste product. You don't have any carbon dioxide here like the combustion engines. Also, it converts most of its stored energy into kinetic energy. So no heat energy waste like the combustion engines, and it's more environmentally friendly. However, when we say that the only waste is water, there is no carbon dioxide, it doesn't mean that it's carbon neutral. Why? Because the hydrogen and oxygen that itself that we use, they can be generated from the electrolysis of water, and the electrolysis of water would need to use electricity, and to use electricity, you need to burn fossil fuel, which means you would need to produce carbon dioxide, so it's not absolutely carbon neutral 100%. And also one of the challenges with the use of hydrogen fuel cell is the cost of production and the storage and transport for